Hi everyone. So in this video, I'm going to talk about how you can carry out geo experiments, and geo experiments are a very important part of modern day testing. If you are into performance marketing or any kind of data driven marketing, you would definitely want to understand how geo experiments work. Geo experiments have become the absolute gold standard in the industry for carrying out incrementality testing. So if you are into incrementality testing and you want to understand how much each channel is worth incrementally, so for instance, how much if will be the additional output in terms of revenue by adding an additional dollar in each channel, this is what you have to do. So there are actually two ways to carry out testing. Traditionally, one is the A/B testing. So A/B tests, you must be already familiar. Even the ads platforms themselves have inbuilt A/B testing functionality, but that requires a certain thing which is called randomization. So you will have to randomize, users, and the randomization at the user level is difficult. You will have to use the platform's own capabilities usually to do that, or come up with a really advanced technical solution to do that. Even then it can be pretty challenging to do so. So in marketing, it's much easier to do randomization, or at a geo level, or just carry out geo experiments in other ways. So we'll just talk about those. And just to go back to the point about users, just tracking whether or not it's the same user is very difficult. You must already be aware. That's why randomization of users is so hard to do. However, that still remains absolutely at the top of the at the top of the list of methods in terms of its accuracy, in terms of being an absolute gold standard, an accepted gold standard in industry. So that is definitely something that you should keep in mind. So let's start with this diagram here, and what I'll do is basically talk about the different methods. This will not be a very technical sort of a session. The whole point of this session is to give you an overview, a quick overview. So this is first of all the traditional geo holdout test, and you'll see that it holdout splits geographical regions into treatment and control groups. So the whole point of holdout is simply to pause something that's already going on. So you want to understand the effect of something that's active in the test regions, and you want to simply pause the effect of anything of that thing in the control region, so the control geos. So on the left hand side, you see what is the traditional A/B testing setup, where you have the entire population, say millions of customers, which are split into test group A and test group B, which I just spoke about, and also its challenges. On the right hand side is the sort of more feasible alternative, which is the geo experiment, where you have the split up into test and control regions. In this case, in this image, you have test group A, test group B. You could have a multi-cell test, for instance, as well, like one control and then two test interventions, one a regular, one an enhanced format, something like that. So perhaps this is pointing towards that, but the idea here is that you split up between test and control geos, essentially, rather than at the user level. Now the question is, how do you select those geos? I think that's exactly the, you know that's precisely the most important, and perhaps that is where it also becomes a little bit more technical. So the region selection is all about it. It all boils down to selecting comparable geographical units, and this can be DMAs, as is the case with the United States, zip codes, cities. It can be at any level of geographical unit, at any geographical level at all. But the point is that you will have to consider costs, you have to consider comparability, and all these factors. So there are certain technical methods, and pre-treatment matching is important in this context. So you have to use historical data. So you have to use two types of data. One is historical data. The other can also be demographic data, like say population or income levels, and you have to use these two to carry out this matching between the geos. So again, just to clarify a little bit more, control geos and test geos should be comparable. That is what we are trying to do, right? I mean, you cannot compare apples with oranges. We also need random assignment, and again, this is something that may or may not be always possible. So random assignment of the treatment to the different geos. So again, this is the ideal scenario, and we'll just come to this in a moment why this is very difficult. So this means that you have suppose a collection of control and test geos, and then you decide, or rather you actually you have a set of geos, and then you decide randomly which of these actually get treatment. In many cases though, that's not how it works. You just decide because you have you decide on the test regions because you have a specific business objective in mind, or you have specific business constraints. Maybe you cannot run in some geos, maybe there's a special offer going on, maybe there are some KPIs to be met. So those are real world constraints which actually make geo experiments harder because of this particular requirement of randomization. And then you apply the treatment, and then you measure the outcomes. These are obviously very understandable, as you can very very self-explanatory. And then comes the final part, which is analysis, which is a statistical analysis. I was thinking I'll probably not go into the statistics in this video because it's going to become much longer. So I'm going to make another separate follow-up video on the statistics part. But what I'm going to really talk about is the different methods. So I hope this was clear. This was the overall idea of the traditional geo holdout test. And now I'm going to just move on to the next phase, which is going to be the different causal inference methods. Now, there are certain alternative methods to carry out in carrying out geo experiments. This was the traditional holdout test, but without actually doing this geo holdout per se, you can still carry out geo experiments or geo experiment like experiments using certain causal inference methods. Now, causal inference is a branch of economics and statistics. It has been around for a while, but it has started becoming very popular now. I've already talked about it in my previous videos. Lots of other material from other experts out there. If you wish to explore more on this, definitely give that a go. So the idea is that you are trying to understand what truly causes something else. So that's where it really comes from, causality. And what you see in front of you is a typical diagram, which is called a directed acrylic graph, or a DAG diagram. This is very typical of how causal inference is represented, or causal linkages are represented. So this is just to get you familiar with certain terms here. So you have controls, you have treatments, and you have KPIs. So essentially the treatment is the assignment of the effect, and you are trying to understand the effect of that treatment, which is often called the average treatment effect, or ATE, in causal inference balance. So treatment and its effect on KPI, and the treatment and the KPI both are getting also affected by the controls. So that is what your control variables are. So this is a typical DAG diagram. I'm not going to try to break it down for you. The DAG is a pretty extensive topic, and probably requires a much in-depth understanding. But like I said, this is not going to be very technical, but this is to get you started, even if you don't do it yourself, so that you can work with a measurement expert, and you can start actually implementing geo experiments. Because I'll take a couple of steps back here, and just point out that I've seen so many marketers actually shy away from getting into the world of analytical experimentation and scientific experimentation, because all of this technical jargon seem to scare them away. But that's what I'm here for. That's what this video aims to dispel. The fears are baseless. You can understand the basics without jumping too much into the technicalities. The second one that I'll dive into is synthetic control method. So that's straight away after your traditional geo holdouts, and this is something that already a lot of tools in the market. So suppose you're working with some tools also, you have to understand what's going on in the back end, right? What's really happening, how they're even doing that. Suppose in most cases they will actually not require you to do any proper geo holdouts, because like I said, it has to be randomly assigned to certain geos, which is difficult because you will have like I said, and you would understand certain business requirements for those tests to be applied to certain regions. You will have business logic behind that. In such cases, you will almost certainly have to do some sort of synthetic application, or choice of coming up with the geos. And one of those methods is the synthetic control method. Again, it's a causal inference method, and this is from a very popular book by Matthias Fakure. And you can see from the image here that this red line here, this is what was happening prior to this intervention, which happened in the dotted line. So this is a famous cigarette related policy that became very popular, and a much studied topic in research, and even in applied academics, which is called Prop 99 or Proposition 99, related to implementing some cigarette related taxation in the United States, in California in particular. And it was seen that after the application of this new taxation on cigarettes, it actually started falling. The adoption of cigarettes, or the purchase of cigarettes, it basically started falling. Otherwise, if it had not been there, so that is being measured by the red line, so that's called the counterfactual. So what if that intervention didn't happen, then what would have really happened? That is what the red line is giving you. Okay, so again, I mean, this is there's more to it, but this is the basic idea that had the new policy not been introduced, then it would have followed the red line's path. But because it followed the path of the blue line. And there's difference between this counterfactual and this actual output after the intervention gives you the effect of the treatment. So this red line here, that has been constructed using synthetic control methods. Now, synthetic control is nothing but a weighted combination of control regions that resemble the treated region's pre-treatment characteristics to construct a counterfactual. So in this case, just to simplify that mouthful that I just said, it means that a set of synthetic controls was actually created to mimic California. And so again, those have to be very similar, and that is done mathematically. So a treatment unit is selected. So in this case, you have only one treatment unit that has to be remembered, or it can be like an aggregate of several, but it will be treated as one entity. And then you have something called a donor pool. The donor pool is nothing but several control regions which are not exposed to the treatment. Now, instead of having one or two control regions, it will basically create a synthetic combination of several such control regions, and that will be done using weighted average, basically. So if you dive into it deeper, it's nothing but actually a form of regression. Eventually you'll see that. But anyway, and regression in itself is actually nothing but weighted averages. It's a glorified weighted average system. But anyway, that's for the more mathematically inclined. Even if you don't quite follow that, the whole point is that you are basically assigning certain weights to different regions. A combination of control regions gives you your ultimate collection of synthetic controls. And this is basically, as you can see, the mathematics behind it, if you're interested in it. This is, as you can see, the for the counterfactual, for the treatment region, during the treatment period, what would have happened. So that is basically given by, because this is something that you don't know, right? You cannot know what would have happened if the intervention didn't happen. So that is what you have to estimate somehow, and that is estimated using this mathematical formula of the synthetic control. So the W here stands for the weights, and the Y, these basically stand for the different values of the treatment, of the outcome rather. So yeah, this is the ultimate formula. So basically what happened exactly after the treatment, and what would have happened, which is given by this formula on the top here. So that's your mathematical formulation. Like I said, again, I just give you a small introduction, but I'm not going to go deep into that. Now comes difference in differences. Difference in differences is again a very popular, relatively simpler method, I'd say. And the concept is very similar. You'll see a very similar kind of graph repeating itself for the causal methods. So you'll see that in this case, the assumption here is that you have very similar trends in both of the control, in the control and the in the comparison group and the intervention group. So for instance, the constant difference in outcome, and you'll see that the constant difference in outcome is carried through to the post intervention period as well. And because of the intervention now, so once again, you have a comparison group and you have a treatment intervention group or a treatment group. And essentially the blue line here, the vertical line, stands for the intervention, and the difference in difference is basically calculated by the difference here that emanates or sort of comes about because of the intervention effect. So you have the intervention effect here that gives you the difference from what would have happened without that intervention, which would have been a constant difference in outcome. So essentially this is how you do it in the form of a regression. So you take two variables, two sets of variables really. Apart from your outcome variables, one is whether or not there was a treatment, so it's like a binary, zeros and ones, and you also have whether or not it actually was in the intervention period. So that there also it's like zeros and ones only. So one of the things here is that there's a very strong assumption of parallel trends. So this is the parallel trends assumption, which is very central to difference in differences. And you'll see that the we also had a very similar assumption here for synthetic controls, obviously, but because we tried to mathematically established similarity. Here you also have that assumption that these two regions would have to be, that is the region in the intervention group and the comparison group, they should be following the parallel trends assumption. So they do not have to be at the same level of output. By the way, this is for instance sales, so outcome, as you can see in the y-axis. Again, this can be sales or contribution margin or whatever it is that you're trying to really measure. They should follow a parallel trend. Like if it's going up, it should go up at a similar slope. So that's basically a parallel trends assumption. Again, this is something that has to be verified before the actual activation of the principle is done, before the actual analysis is done. Otherwise the model is not applicable. Now the causal impact by Google. Now we're coming to established packages. So far, what couple of things that we have seen is they are basically generic concepts, and there are multiple sort of ready-made packages for this. Now what we're looking at is essentially a Bayesian time series concept called causal impact. So Bayesian is a method, an approach, or a framework. You can say it's a massive field within statistics, as opposed to something which we most of you would have been familiar if you have some sort of exposure at least to statistics, I'm assuming at your school level or at some level, which is called the frequentist branch of statistics. So this uses Bayesian statistics. It is very powerful, and it is it has its own merits and demerits. Not going into that, but the point here is that it just sort of simplifies like much of Bayesian. So essentially what you need to provide here is time series data with pre and post intervention period. So that's basically you need to have at least at the bare minimum the dates, and including, you should know what the date of the intervention is, and then you should also have the outcome values. But you also need to have some covariate values, or control variables as well. So what could possibly have impacted the outcome, but these should not be impacted by the intervention or treatment. So that's the definition of the controls. And this basically learns from the pre-period and then predicts what would have happened without the intervention. So basically it's trying to understand what the counterfactual would have been. So that's the whole idea behind it. And once it learns from the counterfactual, it understands the counterfactual, it can then forecast what would have happened without the intervention. So basically that difference between the observed and predicted values within certain uncertainty bounds, of course. So there's always going to be certain level of statistical uncertainty that gives you your causal impact output. So again, this is how it looks like. Just to give you a graphical thing. So this is what was going on in the pre-intervention period. Now you have your observed, and then you have your counterfactual estimate, and the difference between these two gives you your causal effect. So you need univariate time series for treated unit, and it's less transparent because, like I said, this is a package. This is a model which is ready made to be used, and this is available in R and Python. So yeah, this is open source. Now we get to another method. Again, not necessarily a package. There may be other packages, like tools or software, I can say, which are available using this method, very commonly used in this sort of scenario. So propensity score matching, it's called. And you have controls and treatments. But the idea here is that you're trying to compare treated and untreated individuals who are as similar as possible. The idea is again the same, but it's like creating a fair comparison of apples to apples when it's not really apples and apples that you're talking about. So let's look at this overview part here. So it estimates causal effects by matching treated and controlled geographic units based on their probability of receiving treatment given observed covariate. So it kind of flips the thing on its head. So instead of actually looking for geos to give treatment, it's trying to understand, uh, given certain values or variables, how probable it is to get a treatment. Okay, so it kind of flips the thing on its head. If that helps you understand, at least it helps me understand it that way. So in geo experiments, treatment is often not randomly assigned. Remember what I just said at the start when we are talking about the holdout tests, that random assignment of treatment to different geos is very hard to do, because in business, real life business, real world business, you'll probably not be able to do that. Okay, so for instance, marketing teams might choose higher performing series for a campaign, right? I mean, that's kind of obvious, because you don't want to have high opportunity costs. Like, okay, so we ran a test, and it was a complete fluke and nothing came out of it, so we wasted money. We learned something, but we also wasted money, and literally that's hurting the business. So you have to take those things into consideration as well. So that's precisely why these kind of methods are useful. This creates confounding. So this means that when it's not randomly assigned, now the question arises as to what happens when you don't randomly assign treatment to different geos. This means that treatment and outcome now both may depend on factors, which affect the region. So for instance, income, medium income levels, or population levels. So the treatment may not be the only factor. Like for instance, there's good sales from a certain region. Now suppose you have chosen a few regions. Suppose you have chosen some of the bigger geos. Yeah, okay, I mean that's very common. Now you've also got good sales from them, and you've been historically getting them, and from the test also, that's what happened. But the question actually arises whether there's selection bias. Like, did it happen really because of the treatment? Like, by treatment again, we really mean, is it because really of the campaign, or is it because the people are naturally wealthier there, right? Or yeah, so is it because of that? So how do you really determine that? So in order to determine that, this is where, or to sort of isolate that effect, you can't determine it entirely, but you can isolate that effect of the other factors by basically trying to estimate the probability of each region of getting that treatment. And that estimation is done using, usually a very common method here is logistic regression. Okay, so it's like, the probability of treatment is essentially a function of these different methods, and then you match them. After you do that, then you match the different units. You can use different kinds of methods for doing it. You can use clustering, you can use nearest neighbors, different kinds of matching techniques like kernel matching to pair the treated and controlled regions. So you have the probabilities for each region. Now you match, of receiving treatment. Now you match them, and then you assess the covariate balance after matching. Right. And then finally, you compute the average treatment effect on matched samples. So, yeah, this reduces covariate bias. It works with observational geodata. It only adjusts for observed confounders. That's one of its cons. And its matching quality depends on the available covariates. That's a very important point. I think probably one of the most important points, because often when you're trying to do this kind of analysis, you really need good data. And that actually depends on its availability, right? So for instance, whether or not you actually have the data for different things like income and population. In most cases we'll get income and population, but there can be other things like weather variation and stuff. So there will be many information will be available to you, but there may be other factors that you're simply overlooking here. So that actually kind of still means that the problem that you were trying to solve is still kind of remains, right? Because in the previous case, what was happening is you were trying to remove the confounding because of the different factors within the geos themselves, right, which may have affected the sales or the outcome, uh, and not just the treatment. But in this case, that kind of still remains because you're not able to isolate all those factors. But anyway, that's always going to happen. There's always going to be some drawbacks, but propensity score matching is still a very powerful method. The only drawback, I would say, compared to some of the other methods that I just discussed a while back, is that it's a little bit more technical. Okay, because you have to do that regression and stuff. So quite a few things that you have to do together, as opposed to something like say causal impact, which is like a ready-made package for you, or even differences in differences, which is less complicated. All right, so let's move on to the next one. I think we are just coming towards the end. Hopefully you're still with me, and congrats if you are, because I hope that I'm pretty sure you're learning a lot of good stuff here. So I'll move to the next one, which is called the interrupted time series. Again, a causal inference method, and the concept here is kind of similar to difference in difference, except that difference in difference also required a comparison group. Here, you don't have that. It's the same group, and you're basically trying to understand. You're looking at one group over time before and after a specific intervention event, so the interruption basically. So you imagine studying how new speed limit law affects car accidents. This is just to give a simple example. You have monthly accident data before and after the law was passed. You plot the number of accidents over time. If there was a clear jump or drop at the point the law was introduced, it might suggest the law had an effect. So this is again very powerful, and it's very simple, but it's very powerful. It helps you see if that intervention actually caused a noticeable change. So it basically analyzes time series data. So essentially it's like it's one group that you're for which you're observing the sales or the outcome data over time, and then you try to understand, it try to detect the structural breaks at a known intervention period. So it's pre-post period, model trained, assessment of change. These are the different steps in this method here. Now you have another one which is called the regression discontinuity design. Again, a causal inference method. Again, a very similar kind of graph, like I said. But this time, as you can see, it's slightly different here. There's this gap. This treatment effect is now given by this difference in the line. Once again, you're comparing, within the control and treatment, you're trying to compare people just above and below a cutoff point to estimate the effect of an intervention. Okay, so as you can see here, there was an intervention, and then it sort of changed trajectory, so to speak. Now here's a very simple example, and you can easily apply this principle in marketing context. This, you can, instead of a score of an exam in 75, you can easily replace it to say a marketing figure, any marketing metric. So suppose, take this example. Suppose students score 75 or more on a test, get a scholarship. So 75 becomes your threshold point, and then you compare students who got just below 75 and just above 75. And just below 75 means no scholarship, and just above means 75. So these are all almost identical, right? The only difference is whether they got the scholarship. So that's why this is so useful. So any jump in the future grades right at the 75 point mark um, can be attributed to the scholarship. So that's the whole point. Like very similar students now, if they have got a scholarship, you're trying to understand whether or not that actually helps improve future grades. So that's basically a discontinuity. So you're trying to understand whether or not there's a discontinuity. So the treatment and control groups, as you can understand, very similar, because they're both very close to 75 or the threshold mark. And once they're very close to that threshold mark, they're similar. And now you're trying to understand what happens in the future. If the future performance, for instance, really improves, then you know that that intervention most likely had a very, very you know very positive effect. So it gives you a very credible estimate of the treatment's effect right at the cutoff. Okay, so you need a narrow window. So that's one of the things, like you need to focus on regions near the threshold. You can call it local randomization, if that makes any better sense. And you have to have a sharp threshold that assigns treatment to these regions. Okay, and this can be, again, like you need geo level data, suppose for any marketing KPI, and you have to have that cutoff, and you have to have a narrow window, because they have to be comparable. That's the entire thing. The comparability here, very strict comparability, is very essential for this to work. Now there's finally the concept of instrumental variables, which is possibly the toughest concept, and very hard to achieve in reality, um, especially I would say in a context like marketing. So the idea here is this, like, that there are actually two related, there's another related concept, so two concepts very related, instrument and mediator. So let's actually understand instrument first through this very simple, this is also DAG diagram, the first one, very simplest form of DAG diagram. So there's this instrument, and then the treatment sits between the outcome and the instrument. So instrument is something that basically comes before the treatment, and you're trying to understand the effect of instrument on the outcome, but only through the treatment. Okay, so sometimes what happens is you use a third variable that affects the treatment but not the outcome directly, to isolate the true effect of the treatment. Okay, so let's have an example why we would require that. You want to study if more education increases higher income, but people who get more education may also be motivated or come from richer families. Again, kind of like selection bias. So just comparing education and income could be misleading because of that, right? But what if you use distance to the nearest college as an instrument? People who live closer to the college are more likely to attend, but distance doesn't directly affect their income. Okay. So this helps isolate the part of the education that's randomly influenced by college proximity. So you're only going to focus on those people who live very close to the college, and then you use an instrument to, so essentially what it does is it uses an instrument to pull out part of the treatment that's unrelated to the confounder. So again, part of the treatment, because the people who are more likely to attend, that you know the fact that they are that they have a high proximity to their place of education, that has no effect of their income really, right? I mean, at least so goes the understanding. I mean, they could be, if we dive deeper, but this was specifically a research, actually, this example, and this was, I think, this is probably one of the most well sought after research. If I'm not wrong, this actually went on to become a Nobel Prize winning research by Guido Imbens. But anyway, the point here is that to actually understand what instrumental variables really are, or which instrumental variable you should be using, you have to carry out what's called a thought experiment, and it's a pretty tough idea to actually figure out how to come up with a variable that removes this confounding, or which actually helps you pull out part of a treatment's effect that's unrelated to the confounders. So the main thing that it does is that it's useful when there are unseen factors which are messing up your treatment outcome relationship. So it's kind of like a latent variable. It's a variable that's there, but you just don't know it. So you will have to use thought experiments or some mathematical ways of trying to figure that out, but it's pretty complex to do that, and I definitely not recommend it. It's very hard to achieve this. So there are certain methods, several stages to it. You have to first get a variable correlated with treatment but not the outcome, then regress treatment on instrument, then use the predicted treatment to estimate outcome effect, called the 2SLS. So lots of stages here, and finally you have the validation. So here's a nice little comparison table. I'm not going through all of this, of course. Again, I'm going to be sharing this document, if you require it, if you want it, and you might want to go through this comparison table as well. Now I'll jump into the final stage, the final leg of this really long video. Sorry for that. And that's why I said at the start that I'm not going to go into the statistics in this particular one. So now I'm going to just show you how you can actually implement it within the context of, say, Google Ads or Meta Ads. Because if you are a marketer, you already know that you don't really launch campaigns unless very specifically the brand is very geo segregated, you have large number of markets and you're launching them from time to time. So you really would want to think of this, because you don't have campaigns by geos usually. And so how are we going to do that? So like we are talking about different geos, we're talking about controls and holdouts and all, but how exactly do you launch it? So you can have like an existing campaign, like, so you have to first think of, okay, so this is a campaign that I really want to focus on. Like, you would have a business logic that, okay, so suppose this campaign is for a specific set of products, or maybe they are the best selling products, or maybe they're the high margin products, whatever is the logic of creating the campaign. That is a campaign that you want to test. Or it could be that you want to test a completely new idea. If it's a completely new idea that you want to test, then that's fair. But the problem is that if it's a completely new thing, you don't have anything to measure it against as a sort of a yardstick. So oftentimes what happens is you might want to go with a campaign that has happened has happened to work well, has worked well already. So you're now going to test it, a different variation of it, maybe, and you want to duplicate with test regions removed from it. So the idea with the first version of it is that you keep the existing campaign as is. Okay, so you just keep it, and then what happens is the number of campaigns increases. So you had one, now you add two more. So you have duplicate with the test regions removed. So you just duplicate this campaign twice. From the first version you remove the test regions, and from the second you just duplicate with only the test regions, the geos. So now the problem with this is that, again, there's more management work. The number of campaigns increases, but there's a greater chance also of leakage. Like, you don't really want this particular campaign to be shown now to the control regions. That's the whole point of having this first duplication, where you have the test regions removed. But you already have an existing campaign with every geo, right? So because you wanted to keep it untouched, and you wanted to keep it untouched because you didn't want to waste again, have that opportunity cost where you are not showing ads to that region. So so yeah, I mean, that's a trade-off. Like, this reduces the quality of the experiment maybe, but again, from a practical point of view, this is not the best case scenario, but sometimes you may still want to try this with, and maybe have some adjustments. Statistically, it's possible to do that. Maybe you can work with a measurement expert to do that, or whichever tool, if it provides that option, to make the adjustment accordingly, because you have compromised a little bit with the sanctity of the test and the way it should be done with the scientific requirements. But some compromises can also be, adjusted in during the calculation phase. So it's not preferred option from a scientific test point of view, but sometimes this is a more feasible option. The other option is to completely switch off the existing campaign, create a duplicate version of it. I'm sorry, not switch off the existing campaign. I'm really sorry. Just create one new duplicate. The existing campaign does not continue as is, but rather it just is modified to have the test regions removed from it. Now the problem with that is, and the new version, by the way, there's going to be a new duplicate campaign with the test geos. So that's very much like previous case, but this one which you had with control regions, that's not happening anymore. That control is actually the existing campaign itself, because it has the test geos removed from it. Obviously, you can understand what's happening here is that your existing campaign, which had all the learning, that complete goes out of the window, because you have messed with the learning of the campaign. And in many cases it would happen usually, in from a practical point of view, that the test geos will be geos where actually there's good performance. You would probably choose such geos, right? So that, and that's from a statistical point of view as well, because they will usually be certainly larger geos, and the statistical power will be good there, and the duration and the cost of the test will also comes down because of that. With smaller geos, you'll just have to keep testing longer. So, or with geos which don't perform very well, and usually there's an overlap between these. I mean, the performing ones usually are the bigger geos, unless there's some specific reason for it to be different, depending on the business context. But my point here is that you only have one campaign at it, so that's a pro. But a con here is that you lose the learning of the existing campaign, which may not be feasible. So there's this trade-off here. Like, do you want to be, like, be in the good books of data science, and do it from a perfectly scientific point of view, but also keep in mind some level of business logic? On the other hand, you primarily go after the business requirements, and then you compromise quite a bit on the scientific side, but try and quantify that compromise mathematically. Okay, and that can be possible, but there are ways to do it, but there'll still be limitations. But this is what I wanted to show you, like, how you can actually get started with geo experimentation. It's different avatars, the traditional holdout test, and the different causal inference methods. Um, again, like I said, there's a lot of technicality behind it. Of course, there's still a lot of mathematics behind it, still more theory, and definitely far more code and all, which I've not even talked about. Usually these will require some sort of coding and all, but I just wanted to you as marketers to get started with the basic idea, so that you don't run away scared from it and actually start doing tests more scientifically. Even if you do the last example that I gave, where you have some sort of compromise, I think that is still far better than not to have any kind of structured approach to testing. I mean, don't just rely on the existing A/B testing within the ads platforms. They're very limited in scope. Only a few options of testing are there. And secondly, beyond that, also, if you have to test anything, don't just like launch a campaign and call it a test, because you're not really doing it. It's not about being true to what the scientific methods really are, but it's about being true to yourself as well, because you're not doing any justice to your efforts as well. If you are really going to do a test, might as well try and do as scientifically as possible. And but yeah, I've laid out the different pros and cons and the different limitations and challenges. So that was the whole idea. This, like I said, is not meant to be an exhaustive video where you will learn everything, but it's good enough to get you started, hopefully, if you were not already initiated. If you've watched this far, thank you so much for watching, and I really appreciate your time. And if you have any questions, if you have any suggestions on for future videos, I'm certainly going to work on a statistics video as a follow-up to sort of make it easy to understand some important statistical concepts like power analysis and what are the ingredients or the different kinds of statistical tests that are required for validation. That will make it easier for marketers. But yeah, if you have watched this so far, I'm sure you'll be interested in that one as well. And yeah, I hope that you watched that one, and if you have any suggestions, do leave in the comments, and I'll see you in the next video. Thanks for watching.